Hello all, welcoming you all to the topology problem solving session. Today we are going to discuss a problem in topology from Munkres exercise 2.8 P6. It's about quotient topology.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So here it is given that space Rk is the real line in K topology. First let's define that. We know that the space R is the set of all real numbers and whose basis is the collection of all open intervals a comma b such that a is less than b. It's the collection of all open intervals. Now Rk is similarly, the space Rk is similarly the set of all real numbers, but the basis that we have for this space is different. It is just this open interval taken union with a comma b, all open intervals a comma b minus k, such that a is less than b. But what is k? K is the collection of all 1 by n for n in natural numbers. That's like saying 1 comma 1 by 2 comma 1 by 3 and so on. This is our space Rk. So one of the key difference between R and Rk is that if you look closely, the the set K is neither open nor closed in the space R, because 0 is a limit point of the subset K and it is neither open as well. So it is neither open nor closed. But in the space Rk, the subset K is closed. So think about that. So we have that Y being the quotient space that is obtained by collapsing the set K to a point. Let's say that P of K is B naught, is the point B naught. I will have to put a set representation, but that's fine. All the points in K map to the same point. Let's take only B in this quotient map. So what is a quotient map? Let's quickly get through that. So let us take this example only. Rk to Y is a quotient map and Y is the space such that all the set of all real numbers are there, and instead of this K, instead of the elements K, you just remove the elements K from R and add the element B. This is the set Y speaking. But topology defined on this is little different. So the topology is defined in such a way that whenever you have P inverse of U being open in Rk, then it will automatically imply that U is open in Y. And when U is open in Y, it means that P inverse of U is open in Rk. So it is basically saying that these two are equivalent statement. That is, any saturated open set in Rk will map to a open set in Y, and only those saturated open set map to open sets. So that's those two are equivalent. So if you find any saturated open set, then that's the open set in Y. And that is the kind of topology we induce using the quotient map. With that topology, the space Y is formed, and we have to prove that Y satisfies the T1 axiom. What is T1 axiom? It is simple. So let's solve the A part. T1 axiom says that every element of the space, every element of Y is closed. That's what I'm going to prove now. I know the elements of Y are R minus K plus B. We should not write plus, let's write it as union. Every element of Y is closed in Y. So how will I prove this? Simple. The quotient space Y can also be regarded as any subset V is closed in Y if and only if P inverse of V is closed in Rk. So suppose I take any random point other than the point B. Suppose I take a random point from R minus K. Then what will be P inverse of that? Let's say that is V naught from R minus K, which is an element of Y basically. V naught is an element of Y. So what is P inverse of V naught? I know that quotient map takes me from the element to its partition, right? But I know that V naught is identified with V naught only. So P inverse of V naught is actually V naught, because only V naught can map to V naught. Because though V naught is not collapsing with any other point, right? Because it is in R minus K. Only points of K are collapsed. Since V naught is in R minus K, it will not be collapsed, and hence P inverse of V naught is V naught. And we know that V naught is closed in Rk. V naught is closed in Rk. Because you can write like this, right? Minus infinity to V naught, union V naught to infinity. This is open, and the complement of this is closed, which is V naught. And that implies that since P inverse of V naught is closed in Y, and hence every single point in R minus K is closed. But now the question comes, what if your element V naught is B? Then P inverse of B is actually K, right? Because all the points in K collapse to the point B. So that should be the entire set K. Now K is closed in Rk. K is closed in Rk. Because I know that R minus K is open. R minus K is open in Rk. Why? Because each and every element can be put into a basis element that is entirely contained in R minus K. That is A comma B minus K. So hence it is closed. And that implies B is closed in Rk. So hence every element of Y is closed in Y. But Y is not Hausdorff. Why? Y is not Hausdorff. It is actually an important observation. So what I will do, I will say that what is Hausdorff condition? Any two elements of the set, any two distinct elements of the set can be contained in two disjoint open sets. That's Hausdorff. I will show that this is not possible for the elements 0, b of the space Y. If you take 0, b of the space Y, I will now show that any open set around 0 and any open set around B will have some elements in common. Now let's take a closer look into the real line. Suppose if you take 0 to 1 and let's watch it closer. So 1 by 2, you will have 1 by 3, 1 by 4, 1 by 5 and so on. Now I know that any open set around 0, let us call that to be A. Let's call any open set around 0 to be A and around B to be B. Or let's take it to be A0 and B0, some open set. So they are inverse images. Let's take that to be A and B. They are inverse. So basically I'm saying that A is P inverse of A0 and B is P inverse of B0. So I will now show that A intersection B is not equal to phi. That implies P inverse of A0 intersection P inverse of B0 is not equal to phi. And this will directly say that A0 intersection B0 is not equal to phi. Right? Because if it were equal to, because if A0 and B0 were separate, then its inverse image must also be separate, disjoint. If the image, like if two sets are disjoint, then its inverse image must be disjoint under any map you take. So hence, since the inverse image intersection is not empty, we will prove that A0 intersection B0 is not empty and it will not be Hausdorff. So how will I prove that A intersection B is not equal to phi? Let's see what is the form of A. I know that A is open, right? Because A0 is open in Y, which means A is open in Rk. So since A is open in Rk, I can always find a basis element around 0 that is entirely contained in A, and that contains 0 and that contains 0. So obviously since it contains 0, A must be greater than 0, A must be less than 0 and B must be greater than 0 strictly. So that means let's put B here, somewhere here, and A somewhere here, and you have minus K, right? Obviously the minus K is very important because otherwise there will be intersection of this of A and B, obviously, right? Because B, what is B? I know that K is a subset of B. K is a subset of B, right? Because K is equal to P inverse of B. And since P belongs to B0, and since B belongs to B0, I can say that K is a subset of B. So hence, all these elements 1 to 5, 1 to 4, 1 by 3, 1 by 2, 1, everything will be there. So 1 by 6, 1 by 7, everything. Now if this is going to contain the elements of K, if I don't subtract them, then obviously there are some intersection between A and B. Now suppose if I subtract them, even then there will be an intersection. Because I can find sufficiently large capital N value such that 1 by n is less than b, I can do that, right? So let's take this to be 1 by n. So having a closer look, this is your b, 1 by n is here, 1 by n plus 1 is here, and 1 by n plus 2, and so on. Right? Now, since B is open in Rk, because we took a B naught to be open in Y, so B is automatically open in Rk, and hence there is a basis element that contains 1 by n and entirely present inside B, right? And I know any basis element containing 1 by n should be of the form some C comma D around 1 by n. Now clearly see that all the points from 1 by n to D, all the points belong to both, is a subset of both A and B. I mean these points between 1 by n and D. Right? So that will say that A intersection B is not equal to phi, and hence A naught intersection B naught is not equal to phi. So there are few elements. For example, here I could say 1 plus n, 1 by n plus B the whole by 2. Right? The middle element, or like I should take D, the middle element of this blue segment, that will belong P of that. P of that is that only, because that cannot be a 1 by n, because I assume that 1 by n is the smallest such value. N takes the smallest natural number such that 1 by n is less than b. So 1 by n plus d by 2 must be not belonging to K, and hence you can easily see that there is a intersection. So it's not Hausdorff.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.